Okay. Hi everyone. Today we're going to talk about probability. And I know that some people get really kind of upset about math, that they don't want to do math. Oh my God, math is scary. And while probability can get complicated, it's the most useful math concept for designers, and so it's a tool that you need to be able to master and understand. But at the same time, people see probability as, oh my God, look at this thing, it's so complicated, and how am I gonna figure this out and ever do this? I was terrible at math in high school, and that's fine. You can still be that way, but you have to be cognizant of kind of how probability works. You don't have to be an expert in it, but you do need to know what role it plays in games because it plays a significant role. And you'll see that when we get to simulation, but today we're going to kind of go through some of the basic concepts of it. So if you took statistics in high school or anywhere else really, some of this may be old hat to you. If not, then it's going to be new, and there's no way that I can really cover uh, basically a semester's worth of statistics in probability in a single lecture. It's just not going to happen. So I'm going to try to breeze through a lot of these, and if you're a little lost, you may want to look in the book, Google up some tutorials about probability online because there's a lot of really good references all along the internet. But because it is something that really affects how you understand game elements as a designer, random game elements. So probability looks scary and hard like this, but what it really is counting, right? It's counting the things that did happen and dividing it by the things that can happen, and that's the heart of probability, right? And when you put it that way, it's a lot simpler, right? So let's say you want to find the probability of a coin flipping heads. You know, there are two results. That's the things that can happen, and we're trying to figure out how many times heads comes up. Well, that's just one of the two times, so the probability of heads is 1 and 2. There you go, because they happen equally. And so when we write about probabilities, we write in this notation here that I put right here, where I say p, and then parentheses, and then an event, and that means the probability that this event will happen. So given a fair coin that each side comes up evenly, the probability of flipping a heads is 1/2, because heads is 1/2 of heads or tails, and heads and tails are two elements, so 1/2. A probability is usually expressed as a number between 0 and 1. So in this case it would be 0.50. But it can also be expressed as a percentage, between 0 and 100, so 50%, or it can be done as a fraction if it's something simple like this. So how about like rolling a die, right? If it's a 6-sided die, there's 6 sides, the denominator there, the things that can happen is 6. Rolling a 1 is the one thing that can happen, so it's 1 out of 6. So if you're saying rolling a 3 or less on a die, that would be, it means roll 1 or roll a 2 or roll a 3. So 3 over 6 or 1/2. Right? And I hope I'm not talking too fast around this, but very simple concept that we're going to build on here. So rolling a 1 out of 6 chance, assuming a fair die. How about drawing from a deck of cards? Right? So there's 4 suits in a deck of cards, and if we say what's the probability of drawing a spade from a deck of 52 cards, well, there's 13 spades in the deck, so there's ace, king, queen, jack, and then 9 number cards, so that's 13. So 13 out of 52, or 1 out of 4, if you reduce the fraction there. So that's what probability is. It's really figuring out the things that can happen, the things that can't happen, and doing some math on them. But it does require a little bit of thought. It's not, the math isn't hard. It's the wrapping your head around the concept that's hard. So let's say I have a pair of dice, regular 6-sided casino dice like this, and I say, what is the probability of rolling a 7? Right? I'm gonna roll these and add up a 7. Right? So you could say, well, I know this goes up to 12, and since 7 is one of the 12, it must be 1 out of 12, right? And that's one way of thinking about it, but it's not right. And you say, well, it's impossible to roll a 1, right? So maybe it's 1 out of 11, right? Because you can't roll 1 because the lowest you can roll is snake eyes, which is 1 and 1 is 2. So it must be 1 out of 7, or 1 out of 11 to get a 7. And that's not right either. What you have to do is you have to enumerate all possible outcomes before doing the counting. And this is not all possible outcomes. This is all possible outcomes. So this is the 36 ways that 2 dice when rolled can come up. So what's happening in the previous example, oops, let's get through here. In this example, we're condensing all these events that happen into something else. So this 4 and 1 here in the fourth column is a different event than the 1 and 4 here in the first column. So here I have the 36 ways that when you roll 2 dice, something can happen. And we want to say, what's the probability of getting a 7? Well, what you have to do is here's your 36, and you have to count up the ones that equal 7, and that's these here. So the 1 and 6, the 2 and 5, the 3 and 4, the 4 and 3, the 5 and 2, the 6 and 1. So what this is 6 out of 36. So there's 36 possibilities, which is 6 times 6, right? 6 ways the first die can go, and 6 ways the second die can go, 36. And then we just go in and count, and we say 1, 2, 3, 4, 5, 6. 6 out of 36, the answer is 1/6. So this is very different, right, than rolling a single die. A single die has a flat distribution, which is what we have on the left here. It says, given this is given 36 rolls, how many of them end up in that category. And in this one, the theory would explain that it's 6 times, right? And so every bin here, every result is the same probability as everything else. And that's the mistake we make when we go into the 2 dice situation. We say 1 out of 11 because we assume that this is all flat and even. When in reality it looks like what's here on the right. A 7 is the most likely thing to come up, and the 2 and the 12 are the least likely. And this starts to approximate what statisticians call the normal distribution. And we'll talk about that a little bit later or in the book or something, we'll find out. But it's important to know that you have to go in and you have to count up all of the situations before you can just make a snap decision as to whether something works or not. So probabilities are between 0 and 1. And here I have, let's say we're going to take a sample of random people in the United States. We're going to pick a random social security number and we're going to find out what state they're from. Nutmakers are people that are from Connecticut, by the way. I just felt like throwing that piece of trivia in there. So this box here, this blue box, it represents all the people in the United States. And the circles represent the people that fall into these categories. So we have Texans, Ohioans, and Connecticutians or Nutmeggers. And so we want to say, what's the probability that someone is from Texas or from Ohio or from Connecticut? And to do that, we just add up the probabilities. So let's say Texans is 10%, and Ohioans is 5%, and Nutmeggers is 1%. We would just add those together, 16%, and we are done. And that's because none of these overlap. You're either a Texan, or you're an Ohioan, or you're something else, right? Or you're Pennsylvanian, or Floridian, or Californian, or whatever. And that's represented by these circles. Now, when we go and we do something like this, where we say you have people from Texas, you have people from Connecticut, and you have people whose name starts with an H, there's going to be some overlap here. And in this situation, you can't just add the probabilities together because you have these little areas of overlap. So where these circles overlap in here, you're going to count them double, essentially. So if Texans was 10%, Nutmeggers was 1%, names that start with H is 10%, you wouldn't just be able to add 10% plus 10% plus 1% and get 21%, because there's some overlap here in these circles. We're counting these people twice. We're counting them once in the Texans category and once in the name starts with H category. So what you need to do in this scenario is subtract out this overlap. So if the overlap, let's say the total between both the overlaps is 0.5%, we would do 10% plus 10% plus 1% minus 0.5% because these areas overlap. Now, this is a lot, I understand, just kind of going into it if you've never seen this stuff before. But the key feature to understand is that if things are separate like this, you can add together the probabilities. If they're together, you can't add them without subtracting the bonus stuff over. Okay, so And this is when we're talking about or. So we're saying the probability of this or that or something else. And here, and this works for any number of items. So, if we're talking about 10 different categories, and we want to find out what's the probability that somebody comes from a New England state, right? Then we would say the probability that someone is from Rhode Island and Maine and we would add all those together because you can only be from one state or another, assuming. Now, when you want to multiply probabilities, that's when you're using the word and instead of or. So in this one, I have voters, I have Californians, and I have gamers. Some people are voters and Californians, and they're not gamers. Some people are gamers and voters, but not Californians. And some people are all three, right? So if we say we want to know the probability that someone is a voter and a Californian and a gamer, in order to, say, look at their support of the Schwarzenegger bill, what we can do here is multiply these probabilities together. So we would multiply the percent of the population that are voters times the percent of the population that are Californians times the percent of the population that are gamers, and we would get our answer. Now this just like there's a special case here for adding probabilities together where we say these have to be what are called disjoint, that they have to be separate. In this we have another caveat, and it's called independence. We need to be able to say that these things are all independent of each other, that being a voter doesn't affect your probability of being a Californian, or that your being a Californian doesn't affect the probability that you're a gamer. These have to be just events that happen on their own and don't really have any sort of effect on each other. Or if they have an effect on each other, they don't have a different effect than they do on the rest of the population. So in this case, we're talking, like, if you're familiar with football, the punt plays happen on fourth downs most of the time because it's kind of the last resort play. In this case, we know some plays in football are punt plays and some plays in football happen on fourth down. But because it being fourth down affects the probability of whether there's a punt play or not, we can't just multiply these probabilities. We have to do this in a way that forces independence. So in this case, if 25% of plays are punt plays and, well, okay, that wouldn't work so well. Let's say 15% of plays in football are punt plays and 20% of plays in football are fourth downs, we'll say. In that case, you couldn't just multiply these together because most fourth down plays are punt plays. So you would have to separate these out further and just count all the plays in a game and divide them in the way that we did the dice rolls. So this is called independence. This situation, punting is not independent. Choosing whether you're going to have a punt play is not independent of whether you're having fourth down. It's highly dependent on whether it's fourth down. You don't see a lot of first down punts, right? And we're just going to kind of keep going, bashing through these topics. Expected value is probably the most important probability topic that a designer can know, and luckily it's pretty simple. Expected value is given an infinite amount of tries at a game, what is the value of the game? Basically, what is the expected result of the game? So if you had a baseball player whose batting average was 200, meaning 2 out of 10 or 1 out of 5, and he played 100 games, or had 100 at bats rather, you would expect that by multiplying these two together, 100 games times 0.2, which is his probability that he's going to have a successful at bat, means that he would have 20 successful at bats. Right? So we just take, in order to do expected value, we take the sum of all the P events, basically, of all the different events times the value of that event happening. So in the baseball example, the event is does he get on base or not? Or does he have a successful at bat? Because batting average is really, there's some exceptions in batting average, but we'll just say that that's the percentage that he gets on base, even though that's not what batting average is. So let's say 20% of the time he gets on base, 80% of the time he gets out. The value of the event is just 1 or 0. So we're saying, does he get on base? 1, 0, he doesn't get on base. So we would say 0.2, meaning the probability of the event, times 1, and that's one part of the expected value, plus 0.8 times 0, which just sums out to 0, and then you get and you multiply that by 100 because you're going to do it 100 times, and there you go, you have 20 on base. So the reason I put a lottery ticket here is because you can do lottery like this, right? So, and that's just the expanded version here of what I said up there. So let's say there's two events. You either win the lottery or lose the lottery. And you want to know what's the expected value of playing the lottery. How much better off am I given playing the lottery 1,000,000 times or 100,000,000 times or whatever, some large number. Uh, you have to sum the P event times value event uh, of the two states. The two states are win or lose. So here we go. Let's say that you win $1,000,000 if you win the lottery, and that you have a 1 in 2,000,000 chance of winning the lottery. So the value is 1,000,000 because it's what you're saying. You're saying how much better off am I going to be in dollars? That's 1,000,000. Well, let's say the prize is 1,000,000 and $1. 1,000,000 and $1 because we want to pay for the ticket. So at the end of the day, you paid the dollar for the ticket. You won 1,000,000 and $1, so you get $1,000,000. So it's 1,000,000, and the P win here is 1 in 2,000,000. So one win over 2,000,000 plays. And then we want to add the value of the loss event over here on the right. So we have the value, which is -1. You lost your dollar that you paid to get in here. And that happens most of the time. It happens 1.999999 million times out of 2,000,000. So what you do is you would evaluate this math statement here. You would multiply it over. You would have 50 cents on this side minus almost $1 on this side. And the expected value of playing the lottery would be -49 cents. And this makes sense, right? Because whatever the negative event is for the person paying the tickets is how much the lottery makes. So every time the lottery sells a ticket, they expect to make 49 cents. Let's say if this was the true probabilities and values of the games. So you could do this, for any casino game, right? A slot machine. Let's say there's a chance of you winning 10% of the time winning $10 and 90% of the time winning $1. Well, 10% times 10 is $1, 90% times $1 is 90 cents. You add them together, you would get $1.90 as your value of the game. So that means if you were the casino, you would want to set the price of playing above $1.90. And that's how you make money. Every casino game in the world is going to have either a zero but most of the time a negative value to it. So if it's zero, it's what's called a zero-sum game. And like if your buddies are sitting around playing poker, you're just going to pass money around to each other, and there's not really going to be a win or loss component when you sum up everybody. But in a casino, the house always wins is the slogan. That's because they make these games with these negative expected values. So if I was flipping coins and I had, I have this dime and I keep flipping it, and I flip it 4 times in a row and it's a fair coin, and I keep getting Eisenhower's head here, heads, 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 and I say, well, let's have a bet, I will give you $10 if it comes up heads again. How much would you pay for that game? What was the most you would pay for that game? And most people, without a sort of probability education, would say, well, geez, it came up heads 4 times in a row. It's probably going to come up heads again. I'll pay, up to $8 for that game or something like that. And some people would say, well, gee, it came up heads 4 times. It's due to come up tails. I'll pay $8 or I'll pay $2 for that game. And the real answer to this is it doesn't matter what I flipped before because the coin doesn't remember what I flipped before. Every single time it has a probability of 1/2 of coming up heads or tails, regardless of what I flipped before. This is called the gambler's fallacy. And if you go to a casino, and I generally don't recommend it. I mean, I enjoy them, but I know I'm going to lose money when I go. The gambler's fallacy is assigning, making independent events non-independent. Okay? So you're saying, you're playing Dungeons and Dragons and you keep rolling ones in a row and you say, well, geez, I'm due for a hit, right? The dice doesn't know you're due for a hit, right? It just rolls and whatever the probability is the likely event that it comes up. If you if you're a pretty good baseball player and you swing out or you strike out 3 times in a row, you can't say you're due for a hit, right? It's really the same probability, assuming these events are independent. A place you see it is a casino. If you play roulette at a casino, you'll see this board here that I showed, and it's in most casinos that I've seen have had these, and it'll give you a bunch of information. And it's really data. It's not really information. It's really data. And it'll say, like here, if you look at this middle one, it'll say, well, black 17 came up, and then red 12, and then 24, 26, 3. And what happens is the players of these games go, well, gee, look at this run of six black numbers in a row came up. Well, gee, red's about due. I'm going to bet on red. They take this data and they make information out of it, and it's really not information. It's just random numbers. Like here it'll on the left one, it'll say, geez, out of the last 50 spins, black came up 22 times and red came up 22 times, and if that number was disparate, it was like, if black came up 36 times and red came up 12 times, then you would say, to the people that believe in the gambler's fallacy would say, that gives you information. Now I know how to bet. But the little roulette ball that goes spinning around the wheel, it doesn't know this information. It doesn't know that something came up 3 times or 20 times or whatever. It really doesn't care. It's an independent event every spin of the wheel. So you want to be careful not to make this mistake when you're talking about things that are truly independent. Let's talk a little bit about probability trees. This is probably the hardest math that we'll have to do in this class right here is probability trees. And I have a picture of a sock drawer here because this is the kind of standard example for probability trees. So let's say I have this sock drawer and it's a big old mess. And I have 4 white socks in it and I have 8 colored socks. Right, some are red, some are brown, whatever. And I want to pull 2 white socks out of that drawer. What's the probability that when I pull 2 white socks that I will get, or probability that I pull 2 socks, what's the probability that I'll get 2 white ones? Well, you go, okay, kind of the standard way, the naive way of doing this would say, well, there's 12 socks in the drawer, 4 of them are white. My probability of pulling out the first one, of pulling out 1 white one is 1 in 3, right? Because that's 4 over 12. So I just do that twice, right? I do 33% times 33%, and I get my answer, right? I get 1 out of 9, and that would be a mistake because when you pull a sock out of the drawer, you change the probability of what the remaining socks in the drawer are. So imagine I had 2 white socks in the drawer and 100 red socks in the drawer. And let's say I pull out 1 red sock. Well, the probability of that happening is 2%, right? Well, it's a little bit less than 2%. Here, let's make it easier. I have 2 white socks and I have 2 white socks and 98 red socks. There, now I have 100 socks. So the probability of me pulling out that first one and saying the first one, okay, that one's red. No, that one's white. The probability of me pulling out the first one and saying that it's white is 2%, right? I've got two possible white socks in there, so I pull it out. Now, is the probability still 2% that I pull out a white sock? No, because there is 1 white sock left in there amongst 98 red socks. So the probability now is different than it was before I pulled out the first red sock. And so you can answer these questions just by formulating them as probability trees of ways to make them independent events. Because obviously pulling one out changes the probability of the others, so it's not independent. So this is a probability tree. So here's my original question where I had 4 white socks and 8 color socks. We draw this little line. And this line is kind of what we walk down to perform our events. So I can either go down the white path or the color path depending on what sock I pick. And it's a 4 out of 12 chance that I pick the white path, and it's an 8 out of 12 chance I pick the colored path. Now second, I'm going to draw a second sock, right? So I'm going to have another junction here. And so given that I took the white path, I'm going to pick either white or colored again the second time. But the probabilities are different. So I picked 1 sock out, so there's only 11 socks left in the drawer. If I picked a white one first, then there's only 3 white socks left in the drawer, but those 8 colored socks are still remaining. So we would have 3 out of 11 on this branch here, and then 8 out of 11 on the branch below it. Do you see why? So I took 1 sock away from the bottom on both, because there's less socks in the drawer, and then I took 1 away from the white category because in the first pull I pulled a white sock. And we can do that again for the bottom here. But again, the probabilities are different. In this one, the denominator is still 11 because I still have 11 socks left in the drawer. But since I picked the colored one the first time, there's still 4, and there's now 7 colored. Right? Do we see why that is? So now these are independent events because I went through and I have a strict probability for them based on what happened beforehand. So now that they're independent, remember we can go back to our little Venn diagram earlier and we can multiply them. We're saying what is the probability of getting a white and a white, because we're using the word and, right? These are ands, not ors. Or what's the probability of getting a white and a color? What's the probability of getting a color and then a white? Or the probability of getting 2 colors, right? So to do that, you would multiply across. So here we have 4 out of 12 times 3 out of 11, and that would be 9.1%. And that's really the answer to the original question. We said, what's the probability of drawing 2 white socks? There it is. It's actually 12 over 121, or is that right? No, that's not right. 120, 132, I think. 12 over 130. I can't do it in my head. I'm terrible with that. But anyway, you use a calculator and you figure it out. It's 9.1. So if we wanted to find white and then color, what happens? What's the probability that I first draw a white one and then draw a color one? Well, you go down this path and you multiply this and that together like that, and boom, you get 24.2%. So if the question was, what's the probability that I get 1 white sock and 1 colored sock? You wouldn't just go down this path, you would also go down the color and white path and add them together. So this one also, coincidentally, is 24.2%. So you would say you have about a 50% chance. It's actually 48.4. You have about a 50% chance of getting of not getting a match. And then you would say, what's the probability of getting 2 colors? Well, that's 8 over 12 times 7 over 11, and that's about 42.4%. So there's about a 50% chance of not getting a match and about a 50% chance of getting a match. But it's about 5 times as likely to get a match of colors than it is to get a match of whites, even though it's only a 2-to-1 difference in the number of colors in the drawer versus whites. So that's a little complicated. I definitely would request you kind of make up a problem of your own and try to evaluate it in that manner, and you can kind of ping me with it, and I'll try and help out. But so the point of the probability tree is to make events that are independent or that are not independent structured in a way that if one choice comes after another choice, you separate them out to make them independent. So let's do a couple examples here before we wrap up, and I'll leave plenty of time for you to kind of go in and do your own thing. So let's say we have a game here, and there's 4 levels and then like a little end section where you have to beat the final boss. And you want to know what's the probability, how many of my players are going to finish this game? Well, you know that the dropout rate is the same on all of the levels. So it's 10% for level and then 1% on the final part. And so and you're going to assume that these are independent events. Usually in probability examples you assume independence, even though it's sometimes a little shaky. So let's say you have 10% of your players drop out in level 1, then 10% drop out in level 2 and 3 and 4, and then 1% at the end. So in this situation, it's important to know what this 10% is. This is 10% of the remaining players, not 10% of total players. So to go in, you have to kind of figure out how many players are remaining. Well, in each level, it's 90% of the remaining players, and then at the end, it's 99% of the remaining players. Right? So now these are independent events. We know that we want to find, if we're saying what's the probability that they finish, then we're saying what's the probability that you finish level 1 and finish level 2 and finish level 3 and finish level 4 and finish the end, right? The only way to make this a multiplication problem is to form it in that way, where we're saying what's the probability of A and B and C and D and E, etc. So you can't multiply these tens together because this is saying what's the probability that someone drops out in level 1 and drops out in level 2 and drops out in level 3? Well, if they drop out in level 1, they're not around to drop out in level 2, so you can't make that. You can't make that a multiplication problem. So if you change it to be what is the percentage of people that stay, then you can make a multiplication problem. And if you do that, you get 64.9% make it and 35.1% drop out. So there you go. Let's do another example. This goes back to our expected value, right? Let's say you have 4 different types of players. You have the power gamer, you have a skilled gamer, you have just your normal critical path gamer, and you have some kind of slackers. You do a survey and you find out this left column here is the percentage of your audience that fits these profiles. And your average power gamer makes 10,000 experience, your skilled gamer makes 2,000, your critical path people make 1,000, and your slacker people get 500. What should I expect that the average player makes? And that's the expected value. And so what would you do here? Right? I'll give you a second here while I take a sip of my drink. Now, if you said you're going to sum up all the probabilities times the values, you would be right. So what you do is you would do 1% times 10,000 plus 10% times 2,000 plus 69% times 1,000 and plus 20% times 500, and you would get the answer 1,090 experience points. And you'll see, because most of the players are critical path gamers, that the answer is close to that value, and that's kind of how it works. It's a weighted average. Okay, so here's what to do. Read videos, play, and comment, and quiz. I realize that some people they haven't seen this before, so they're going to have problems with it. I do recommend reading the chapter on probability tools in the book, watching this video again if you're kind of unsure, just to kind of cement those together. And if you're still having problems with the ideas in this one, go ahead and send me an email and say, I'm having problems with this concept or that concept or whatever, and I'll get back to you and try to give you some stuff that'll help. Okay. So that's that. That's probability, and it's very useful to players because you're going to have questions like this when you come up in real games. You're going to say, you want to design a quest for the majority of your players. Well, you need to know where the majority of your players are on your experience counts. Or you're going to have something like this, and you're going to say, well, how much time do we spend on this end level if 20% of our players are going to make it there? Well, in order to answer that question and say only 20% are making it there, you need to do this kind of analysis. And this analysis gets a lot easier with Excel, especially this stuff with the probability trees, because you can have Excel do the math for you, right? So if you use the concepts that we did in the last video, you shouldn't have any problem with the math at all because the computer will do the math for you. The problem is in setting it up to make sure that you know exactly what kind of thing you're going to get into. Right? I'm just going back through and make sure I didn't miss anything here. Talked about independence, right? About the gambler's fallacy. Don't do that. The expected value is a very common thing of if I follow this strategy, how many points am I going to get? If I follow this strategy, how many points am I going to get? And that's really expected value. And the whole idea of independence, that's a little fuzzy for a lot of people, so if that's not working out for you, then let me know. And we're going back to the beginning here. And really it's just about counting, right? It's about counting the things that happen and the things that don't happen, and knowing when things are independent and not independent. So, really that's all there is to it. Hopefully that's a reasonable, kind of half-hour, 40-minute approach to probability. But like I said, if you're having problems, you let me know, because our quiz this week is going to be using Excel to answer these questions. I mean, that's going to be a large part of that exam. So let me know, and otherwise, have a good one.